Year 13, Chapter 19, Force and Motion, Lesson 4, Newton's second law of motion. So, you have come across Newton's second law of motion expressed in the form F equals ma previously, force equals mass multiplied by acceleration. We are going to write this as resultant force, so sum of the forces, is equal to mass multiplied by acceleration. Now, because we are looking at forces in multiple directions, we need to be clear that we are talking about the vector sum of the forces is equal to mass multiplied by acceleration, remembering that acceleration is also a vector quantity. We're now going to apply this rule in situations where particles are not in equilibrium, where they are experiencing some sort of resultant force and consequent acceleration. So let's have a look at this example. Now, this is a sort of example you might have come across in year 1, so it's a good review of this content. Let's read the information and sketch a force diagram. So we have two particles, P and Q, of masses 6 kilograms and 3 kilograms respectively, connected by a light inextensible string. P rests on a rough horizontal table and Q hangs vertically. So I'm going to draw the table. Here it is, my rough horizontal table. And here is the edge of that table, like so. And let's add the particles into the diagram. So particle P is at rest on the horizontal table. Now P will have a weight of 6g. There'll be a normal reaction force upwards like that. Now P is attached to Q via a light inextensible string which passes over a smooth fixed pulley. So if this is our pulley over there, the string will pass over the pulley and then will be attached to particle Q. Now particle Q has a mass of 3g. We then need to make sure that we include tension, so tension here and tension here acting on Q and P. The tensions are of the same value because the string is inextensible. Now remember, the table is rough, so there is a frictional force opposing the intended directional motion of P. When the system is released from rest, we know that Q is going to accelerate downwards like that. This will pull P along in this direction. They will have the same acceleration because the tension is constant throughout the string, because the string is inextensible, which means resultant force is constant, which means constant acceleration. Because P is going to move in the right-hand direction, friction will oppose this motion and friction will act in this direction here. So we now have a fully labelled force diagram with a connected pair of particles. We're now going to apply F equals ma separately to Q and to P. So let's write down our law, Newton's second law of motion, and let's start by analysing the forces acting on Q. Q is moving downwards. I'm going to take down as positive. So the resultant force is 3g acting downwards minus t acting upwards equals mass 3 multiplied by acceleration a. What about P? Well, P is moving to the right, so we'll take going to the right as positive. So we have t minus the friction equals mass 6 multiplied by the acceleration. Now, how do we then solve this pair of equations? Well, simultaneous equations, we can simply add these equations together, which gives me 3g minus f is equal to 9a. Now, g is obviously 9.8, but I don't know the value of the friction. However, in the question, there was an additional piece of information which told me that friction takes a value that is 1/3 the magnitude of the normal reaction force. Now, if I analyse the forces on P vertically, well, vertically, acceleration is equal to 0. There is no motion vertically. So forces must be balanced vertically, which tells me that the normal reaction is equal to 6 g. Now the friction is equal to 1/3 of the normal reaction, so it must be equal to 2g newtons. So this gives me 3g minus 2g equals 9a. So the acceleration of the particle equals 1/9 g meters per second squared. And we can work that out as a decimal if we wish. So that's our answer to part A, the acceleration. Now, to work out our answer to part B, we simply substitute into one of these equations that we were using earlier on. I'm going to substitute into this one over here. And T then equals 2g plus 6 lots of A, and that works out to be 8/3 g newtons. Now, the last part of this question, question C, asked us to find the overall force exerted on the pulley. So let's think about the forces acting on the pulley. So the blue tension forces you can see in the diagram are acting on particles Q and P. There must be equal and opposite tensions acting on the pulley. So if I draw the forces acting on the pulley, there'll be tensions like that. You can see them in purple. So here is the pulley, and it's being acted on by a T force like that and a T force like that. Now, to find the resultant of those T forces, let's draw this out again. So here's the horizontal T, here is the vertical T, which means there must be a resultant force acting on the pulley in this direction like that, an overall force acting on the pulley in this direction. So, how do we work out the value of that force? Well, it's equal to T squared plus T squared, all square rooted. And that comes to 36.958 ... or 37.0 newtons to 3 significant figures. So let's take this into the more complex questions that we are required to be able to solve in our Year 2 mechanics content. So we have a particle P, which is of mass 5 kilograms, which lies on a smooth inclined plane at this angle. Theta equals arc sine 3/5. Now, that is not as complex as you might think at first sight. This simply tells us that sine theta equals 3/5, arc sine being the inverse sine. And if we were to draw a quick right angle triangle with theta involved, then the opposite and the hypotenuse would have a ratio of 3/5, 3/5, which would leave the adjacent as 4 in a 3, 4, 5 right angle triangle. So P is connected to another particle Q, which has mass 4 kilograms, by a light inextensible string, which passes over a smooth light pulley. Now, the system is held at rest with Q hanging vertically 2 meters above a horizontal plane. The system is then released from rest. So we have 3 things to calculate here, assuming that P does not reach the pulley. Before we calculate any of these values, we need to draw an extremely clear force diagram and label everything on that diagram. So here's the horizontal plane. And here is my slope. Now, I'm going to put in particle P. Which has a mass of 5 kilograms. Now remember, let's draw in the weight. It's a nice, long, clear force like that, 5g. Let's draw in our angle theta. And let's draw in the normal reaction like that, perpendicular to the plane. Now it's a smooth plane, so we don't need to include a frictional force, but P is attached via a light inextensible string to another particle. So here is the string passing over a pulley, like so. And then we're attached to a second particle, Q. There's Q, and this one is P, which has a mass of 4 kilograms. So Q has a weight of 4g. And let's make sure we include in the diagram tension forces acting on P and Q, like so. We are also informed that Q is released from rest 2 meters above the ground, like so. Now, let's have a look at analysing the motion, making sure that we draw in the components of the weight. So if I draw in a component of the weight perpendicular to the plane like that, let's make a little bit of space here, that 2 meters can be over there. And then let's draw a component of the weight parallel to the plane like that. And then we know from our previous work that this angle here will be theta. Now, when the system is released from rest, Q will accelerate downwards like that, and P will accelerate up the plane like that. Because the string is inextensible, tension remains constant throughout the string, which means resultant force is constant, which means acceleration is constant. And the same for both particles. So we're going to use F equals ma throughout, and we're going to start by analysing the motion of Q. I'm going to take down as positive because that's the direction of its motion. Resultant force, we have 4g acting downwards, so that's positive, t acting upwards, so that's negative. So we have 4g minus t, and that is equal to the mass 4 multiplied by the acceleration. So we have one equation, 2 unknowns, a and t. Now, let's analyse the motion of P next. So what we're going to do is we're going to look at both directions, perpendicular to slope and parallel to the slope, to see what we can perhaps deduce. Now, if we look at P perpendicular to the plane, like that, then we know that forces are balanced, perpendicular to the plane. The particle isn't leaping up off the plane in the direction of the normal reaction force, and it's not burrowing down into the plane either. So what we know is that forces are balanced, and we know that the normal reaction must be balanced by this component of the weight, which I've highlighted in light blue there. So perpendicular to the slope, we know that the normal reaction must be equal to 5g, and look at this blue component here. You can see it is adjacent to that angle theta, so it's 5g cos theta. And if we wanted to, we could work that out because cos theta is 4/5. We could also use a calculator to find out theta and then cos theta. So that would simply be equal to 5g multiplied by 4/5, so 4g newtons. But we weren't actually asked to find the normal reaction. It's just interesting to analyse that motion. Now, what about P in the direction parallel to the slope? Well, parallel to the slope, it's moving up the slope, so I'm going to take up the slope as positive. Let's apply F equals ma. We have t going up the slope, and then we have this component here down the slope and opposite in direction to t. Now that's a sine component of the weight because it's opposite the angle theta. So it is t minus 5g sine theta. Remember, up is positive, so this component, 5g sine theta, is negative. And this then equals the mass of P, which is 5 multiplied by the acceleration a. Now, we know that sine theta is equal to 3/5, so that's t minus 5g multiplied by 3/5 equals 5a. And then, obviously simplifying that, t minus 3g equals 5a. So we have a pair of simultaneous equations which we can solve. So if we do equation 1, add equation 2, that then gives me g equals 9a. So a is equal to 1/9 of g meters per second squared. We can work that out as a decimal if we wish. We can also substitute back in to find the tension, but we weren't actually asked to do that, so we don't need to do that just yet. So the next part of the question asked us to find the time taken for Q to hit the plane. Now, remember earlier we talked about how the string was inextensible, which means tension is constant throughout the string, which means resultant force is constant, which means acceleration is constant. Now, if acceleration is constant, this allows us to use the Suvat equations, our equations of constant acceleration. So let's look at the motion of Q. We know it's travelling 2 meters until it hits the ground. We know its initial velocity is 0 because the system is released from rest. We don't know the final velocity as it strikes the ground. We know that A is equal to 1/9 of g, and T is what we are actually looking for. So this is what we want to find, and we don't know V. So looking at this information, we can then make use of S equals ut plus a half at squared. So what happens when we substitute into that? Well, we can say that 2 is equal to a half multiplied by 1/9 g multiplied by t squared, and we can simply rearrange that to find out that t is equal to 1.916 seconds. So t equals 1.92 seconds to 3sf, so just under 2 seconds before particle Q hits the ground. Now the last part of the question asks us to calculate the total distance that P moves up the plane, assuming that P does not hit the pulley. Now, P's motion up the plane consists of 2 separate parts. I'm going to draw this out in a little more detail. Imagine we're zooming in on the diagram because there isn't a huge amount of space there. So let's imagine this is particle P. And obviously it's attached via this inextensible string to particle Q, etc. But I'm not going to draw in all of that information. Now, Q has to travel 2 meters to hit the ground. Because the particles are connected by this inextensible string that does not stretch, when Q travels 2 meters, P will travel 2 meters. So P will travel 2 meters whilst Q is travelling towards the ground. Now, at this point here, if I sketch the particle P in again, this is the point at which particle Q has hit the ground. Now, when Q has hit the ground, the string is going to become slack, but P will still have momentum. So the string is now slack, the tension is 0, but P has a residual velocity, it has momentum, and it will continue to travel up the slope until it stops. So there's going to be a second phase of the journey up here through a distance, let's call it x, until P comes to rest. And our job is to find out the value of x and then add that to 2. So let's start working this out. So we know that P travels 2 meters up the slope before Q hits the ground. Let's think about the moment when Q hits the ground here with some velocity, and I want to work out what that velocity is. So if you remember, we wrote down that S was equal to 2, U was equal to 0, V we didn't know, A was equal to G over 9, and actually T we worked out it's 1.916 ... So we do actually know the value of T. This time, let's work out the value of V, the velocity with which Q hits the ground. So if we use V equals U plus AT, using the time value that we calculated previously, we can work out that V is equal to 2.086 ... Some people might prefer to work out V using V squared equals U squared plus 2AF, so it's not reliant on a previous value, but I do know that the value T 1.916 is correct, so I'm happy to use that value. Now I'm not going to round this because we're going to use this in subsequent calculations, because not only is this the value of the velocity with which Q hits the ground, it's the velocity of P at this point here when Q hits the ground. They'll have the same velocity. So P will be travelling with a speed of 2.086 meters per second at the moment when Q hits the ground. So let's now analyse the motion of P once Q has hit the ground. So we know that when Q hits the ground, the string now becomes slack and the tension is equal to 0. But we know that because P has this residual velocity here, it's got some momentum which will carry on propelling P up the slope. However, because the tension is now 0, because we're not now dealing with the same situation, same resultant forces previously, P will have a new acceleration, and we need to calculate this new acceleration. So we need to calculate this new acceleration of P. So I'm going to draw a new force diagram very quickly, just to make it really clear as to what the forces are on P. So we're looking at P after Q has hit the ground and the string is slack. Now we'll still have this normal reaction force up here like that. P will still have its weight of 5g, this is still angle theta, and we'll still have these components perpendicular and parallel to the slope, and this angle will still be theta degrees as well. What we no longer have is the tension up the slope. So I'm going to ignore the forces acting perpendicular to the plane, and I'm going to look at the forces acting parallel to the plane. So let's say the acceleration is in this direction. Let's take up the slope as positive, as that's the direction of motion of P. Now, we have no components or no forces acting up the slope, but we do have this component here, which I'll highlight in purple, acting down the slope. So when we apply F equals ma, the only contribution to the resultant force is minus 5g sine theta. And this is equal to m, which is 5 multiplied by the acceleration. So the acceleration is now clearly equal to minus g sine theta. But of course, we know that sine theta is equal to 3/5, so the acceleration is minus 3/5 g. It is, in fact, of course, a deceleration, which makes sense. There's nothing pulling the particle P up the slope anymore. Weight, its own weight, is trying to pull it down the slope, so it's going to decelerate until it comes to a stop. So we now need to find out how far P travels, which is the distance x, before it comes to a stop. So let's apply Suvat to this final journey of P. The distance travelled is x. Its starting velocity, well, we're looking at the period of time between the instant where Q hits the ground and when P comes to a stop. Now, at the start of that period of motion, P is travelling with the same velocity with which Q hit the ground. We worked it out earlier, it's 2.086 ... Now, its final velocity is v, and its acceleration is minus 3g over 5. We don't know the time taken to come to a stop, and we're not actually working it out. So we now need to make sure we use v squared equals u squared plus 2as, and we can calculate the value of s by substituting in and rearranging. And this then gives us a value of s, which is 0.37037 ... So the total distance travelled by P up the plane is the original 2 metres covered by Q before it hits the ground, and this extra distance P travels up the slope before it comes to a halt. So that is 2.37 metres to 3 significant figures. Now, how do we know the acceleration is constant? Well, the only force acting is the weight, or the only contribution to the resultant force is from a component of the weight. Weight is constant, resultant force is constant, acceleration is constant. We can use the constant acceleration equations. So let's look at our next example. We have a particle A of mass 0.5 kilograms resting on a smooth plane, which is inclined at an angle theta equals arc sine 3/5. Now, we know how to deal with theta equals arc sine 3/5. We've seen something similar to this previously. Let's just draw in a right-angled triangle, and in our right-angled triangle we can label our angle here theta, and we know that this simply means that sine theta is equal to 3/5. So we can say the opposite could be 3, the hypotenuse 5, and then that leaves our adjacent here as 4. So what else do we know? A light, inextensible string is attached to the particle and passes over a smooth pulley at the top of the plane. A second particle of mass m hangs freely from the other end of the string. The system is released from rest with the string held taut, and then B descends 1 metre in 1 second. We have got to calculate the value of m and the tension in the string. So, what are we going to start off by doing? We are going to sketch a very clear force diagram. So, here is my slope, inclined at an angle of theta. And we're going to draw in particle A, which has a mass of 0.5 kilograms, so a weight of 0.5 g. We know that there's a normal reaction force acting perpendicular to the plane like this, and it's a smooth plane, so we don't have to take friction into account. Here's the pulley, a smooth pulley at the end of the plane, and there's a light, inextensible string passing over the pulley, attached to A in one end, and then at the other end it is attached to particle B, which has a mass of m, so a weight of mg. Let's then put in tension force here, pulling A up the slope, and a tension force here, like that. Now, when the system is released from rest, we know B will move downwards, so will accelerate down in a vertical direction. A will accelerate up the slope like that. We know that B descends 1 metre in 1 second. So we are going to make use of resultant force equals mass multiplied by acceleration. And we're going to start off by analysing forces acting on B. So B moves downwards, so it makes perfect sense to take down as a positive direction there. We can then say that the resultant force, mg minus t, is equal to ma. Now at this point we have a lot of unknowns, m, t and a. So even when we analyse the motion of A, we're still going to have to do something else to solve this problem. Let's move on to particle A. Now I'm going to draw in components of the weight perpendicular to the plane and parallel to the plane like that. And here is the angle theta, as we know. Now we know that this component here, I'll highlight it in orange, is a cos component, so that's 0.5 g cos theta. And then this component here, which I'm going to highlight in pink, which is parallel to the plane, is opposite the angle, so it's a sine component, 0.5 g sine theta. Now, we know that perpendicular to the slope, normal reaction just equals 0.5 g cos theta. Perpendicular to the plane, forces are balanced. We're not going to actually really look at that motion. What we're going to do is look at the motion in this direction, taking up the plane as positive, and we're going to apply F equals ma again. We have t up the plane minus 0.5 g sine theta down the plane. Those are the only forces or components of forces which are parallel to the slope, and this equals the mass 0.5 multiplied by the acceleration. And again, we have t, a and m as unknowns, so we can't do very much more for the moment. Now let's come back to the motion of B, and let's think about applying our Suvat equations here. We've discussed previously if the string is inextensible, tension is constant throughout the string, which means resultant force is constant, which means acceleration is constant, and the same for both P and Q. So B descends 1 metre in 1 second, so we can fill in those values. The system starts off from rest. We don't know V and we don't know A, but we do want to find out A, whereas V we're not interested in at the moment. So we can make use of S equals ut plus a half at squared. 1 is equal to a half a multiplied by 1 squared, which simply gives us a equals 2 meters per second to the negative 2. This then allows us to calculate t and then to calculate m. So if I label this as equation 1 and equation 2, let's see what we can then work out. So from equation 2, we know that t minus 0.5g, now we know that sine theta is 3/5, is equal to 0.5 multiplied by a, which is 2. I can rearrange this and I find that t is equal to 3.94 newtons. And then if we substitute everything we know into equation 1, we know that mg minus t, 3.94, is equal to 2m, because the acceleration is equal to 2. We can then combine m terms on one side, so mg minus 2m equals 3.94 after some rearranging, factorise, and then divide through by g minus 2 to give us the value of m, which is 0.50512 kilograms, or m equals 0.505 kg to 3 SF.